Welcome to this tutorial on Kubernetes troubleshooting. Today, we're diving into one of the most common issues you'll encounter: pending pods and scheduling failures. Understanding why pods remain in a pending state is crucial for maintaining healthy Kubernetes clusters. By the end of this video, you'll know exactly how to identify, diagnose, and resolve these scheduling problems. Let's start with the basics. A pending pod is a pod that has been accepted by the Kubernetes cluster but cannot be scheduled to run on any available node. When you create a pod, it goes through several lifecycle phases. It starts in the pending state, then moves to running once it's successfully scheduled and started on a node. After execution, it can transition to either succeeded or failed. If your pod is stuck in the pending phase, it means the Kubernetes scheduler cannot find a suitable node to place it on. There are four main categories of issues that cause pods to remain pending. First, insufficient resources, which occurs when nodes don't have enough CPU or memory available. Second, node selection issues, where node selector, affinity, or anti-affinity rules cannot be satisfied by any node in the cluster. Third, taints and tolerations problems, where the pod lacks the required tolerations to run on nodes that have been tainted. And fourth, volume and image issues, including unavailable persistent volumes or failures when pulling container images from registries. The most common cause of pending pods is insufficient resources. This happens when no nodes in your cluster have enough CPU or memory to satisfy the pod's resource requests. When you describe a pending pod using kubectl describe pod, you'll see events showing messages like failed scheduling, with details such as 0 out of 3 nodes are available, 3 insufficient CPU, 2 insufficient memory. The scheduler tries to find a node that can accommodate your pod's resource requirements. But if all nodes are already heavily utilized, the pod will remain in a pending state until resources become available. Node selector mismatches occur when a pod requires specific node labels that don't exist anywhere in your cluster. If your pod specification includes a node selector demanding labels like disk type equals SSD and environment equals production, but none of your nodes have these exact labels, the pod cannot be scheduled. The event message will clearly state, failed scheduling, with a note that nodes didn't match the pod's node affinity or selector requirements. This is a configuration issue that requires either updating the pod selector or adding the appropriate labels to your nodes. Taints and tolerations provide a mechanism to control which pods can run on specific nodes. When a node has a taint applied to it, it rejects all pods unless those pods have a matching toleration. For example, if a node is tainted with a key of node role, value of database, and effect of no schedule, only pods with the corresponding toleration can be scheduled there. Without the required toleration in the pod specification, the scheduler will skip that node entirely. And if all suitable nodes are tainted, your pod will remain pending. Affinity and anti-affinity rules give you fine-grained control over pod placement. Affinity rules attract pods to specific nodes or help co-locate pods together on the same node, which is useful for performance optimization. Anti-affinity rules do the opposite. They repel pods from certain nodes or spread pods across different nodes for high availability. When you define required affinity or anti-affinity rules in your pod specification, and those rules cannot be satisfied by the current cluster state, your pod will stay in pending status until the conditions are met. Pods that require storage through persistent volume claims can remain pending for several reasons. First, there might not be any persistent volume available that matches the claim's requirements in terms of size, access mode, or storage class. Second, there could be a volume zone mismatch, where the persistent volume exists in a different availability zone than the node the pod is trying to schedule on. Third, dynamic provisioning might be taking longer than expected to create the volume. Until the volume is successfully bound to the pod, it cannot transition from pending to running state. Image pull errors can also cause pods to appear as pending or show image pull backoff status. There are 4 common reasons for this. First, missing registry credentials, when your cluster doesn't have the proper image pull secrets to authenticate with a private container registry. Second, the specified image simply doesn't exist in the registry. Third, an incorrect image tag was specified in the pod definition. And fourth, network connectivity issues preventing the node from reaching the container registry. You'll typically see error messages like failed to pull image, followed by error image pull or image pull back off. Let's look at the essential commands for troubleshooting pending pods. First, check the pod status and events using kubectl describe pod followed by your pod name. Pay special attention to the events section at the bottom, which provides detailed information about why scheduling failed. Second, view cluster-wide events sorted by timestamp using kubectl get events with the sort by parameter set to last timestamp. This gives you a chronological view of what's happening across your cluster. Third, check node resources using kubectl top nodes to see current resource usage, and kubectl describe node to view detailed information about capacity, allocatable resources, and any taints on specific nodes. Now that we understand the causes, let's discuss resolution strategies. For resource constraints, scale your cluster by adding more nodes manually or enable cluster autoscaling to automatically adjust capacity based on demand. For node selection issues, fix labels and selectors by ensuring node labels match your pod selector requirements exactly. For taint and toleration problems, update the pod specification to include the necessary tolerations that allow it to run on tainted nodes. Finally, for dependency issues, resolve volume bindings by creating or provisioning the required persistent volumes, fix image registry access by adding proper credentials, and troubleshoot any network connectivity problems preventing image pulls. Let's recap the key takeaways. First, remember that pending pods indicate scheduling failures, not application errors. The pod itself may be perfectly fine, but the cluster cannot find a suitable place to run it. Second, always check events using kubectl describe as your first step in root cause analysis. The events section provides invaluable information about exactly why scheduling failed. Third, resource constraints are the most common cause of pending pods, so monitoring cluster capacity and implementing autoscaling is crucial. Fourth, node selectors, taints, and affinity rules must align with your actual cluster state. Mismatches in these configurations are frequent sources of scheduling problems. Master these concepts, and you'll be able to quickly diagnose and resolve pod scheduling issues in any Kubernetes environment.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.